Hi, everybody. Sorry for the late. I wait others participant, and yes, we can start now. I will share the screen, my screen. Okay. And also, firstly, I want to say this video is recording and. Okay. Yes, this meeting is our second meeting. In this meeting, we will talk about today what we did and what we'll do next step of our project. First step, of our project is to load the image to be stored as a quantum state. For this, we use four model and to compare the accuracy result of our application. First, novel enhanced quantum representation. Second, quantum Boolean image processing. Third, quantum probability image encoding. And fourth, flexible representation of the quantum images. I want to, from you, all of you, a little explanation what you do for 2 weeks. Is there anybody start to share their work?
Hello, Dr. Kochak. I may start.
Okay.
Our project was about trying to use the novel enhanced quantum representation, and our theme consists of me and Gabriela.
Yes.
And at the previous week, we read the original paper about the novel enhanced quantum representation, and also the documentation you sent about that the general information about quantum image processing, which is published by Fraunhofer Institute. And so from today for the next week, we are going to try to implement that operation in Python and try to load images.
Okay. Okay. Next, who will start?
I can continue if it's okay.
Okay.
So I tried to implement the FRQI technique.
Yes.
The flexible representation of quantum images, which is a technique that uses the least amount of qubits, which is good in terms of efficiency, but it's not good because it's also the least accurate among other techniques, and it can also be hard to recover the original image in this technique. So what I have done is I tried to work with the images. I first tried to work with only one image from the data set we are working with. I mostly figured out how to implement the circuit, but like I'm not very knowledgeable about how to translate a mathematical expression into a quantum circuit. And I also have written to you regarding that. So I mostly implemented the algorithm, but I only like how to encode the pixel intensity to the ancillary qubits. So if I have figured that out, I think I will be mostly done with the algorithm, and also with only one image. If it works for only one image, then it should also work with the other images. So yeah.
Okay, thank you. Okay, third.
Yeah, hi. I and Shimge, we do worked on the quantum probability image encoding.
Mhm.
Maybe Shimge, can you share the screen,
Okay.
like the presentation? Yeah, so maybe a just quick summary that what is this quantum probability encoding thing, just to make everyone aware of this one and we are on the same page. So basically here the image, the pixels of the image, which is in the grayscale for this handset data set, we try to encode that into the amplitude of the quantum state. So if we have n cross n pixel, then we try to encode. Then we have to encode that into 2 times the log n base 2 qubits. So can you go to the next slide?
Okay.
So we try to now do the two. We try to create the two sub functions for this image encoding. The first one is the loading the data set and doing some pre-processing steps so that we will be able to encode that into the quantum state. And second one is the QPIE encoding function. Can you go to the next one?
Okay.
Yeah, so this one is the normalization of pixel values. So what we did is we started with this function, which is this QPIE encoding function. So which takes an image as an input. So this image is basically a binary matrix because we are working with the grayscale image. So all these 0 and 1s. Then we try to normalize it. So why we normalize? Because the amplitude of the state, quantum state, has to give the norm 1. That's the definition of a quantum state. So that's why we have to normalize it. And then we encode all the pixel values, this n cross n pixel values, into the amplitude of the quantum state. Can you go to the next one?
Yes.
Then we have this encoding of quantum state here. So if we see, once we have this image vector ready, which is kind of flattening the matrix. So we have n cross n matrix, but since we have a vector, so we have to do the reshaping of this matrix. So we do the reshaping of the matrix, and then we initialize the quantum circuit with that quantum state. And here is one example which is shown on the screen. We have this image, and then we converted that into the circuit, and we have to use 12 qubits because this is 64 cross 64 image, so that will be 2 raised to 12. So that's why we have to use 12 qubits here, which is shown on the right hand side, initialize and all these zeros, and it will be a long vector, 2 raised to 12. Yeah, thank you. So this is the work that we both did last week, and we'll continue on this QPI encoding further to do with this quantum machine learning. Yeah, thank you.
Thank you. I want to ask something. When you measure your circuit, can you get the original image? It's so close or not? Did you test?
Pardon?
Have you ever measured your circuits? When you measure, you get the original image?
So we didn't try that measuring and then getting the image because we didn't try that one. We just encoded that and we just tried to see whether our initialized circuit is correct or not.
Okay. Thank you, all of things. And finally, fourth.
Yes. Can I share my screen?
Yes.
Before presenting my own algorithm, I would like to introduce myself.
Okay.
Last week, I couldn't attend the meeting as I had some matters to attend to at the hospital, so I apologize for that.
Get awesome.
My name is Asude Ertan, and I am computer programming student at Istanbul University, Cerrahpaşa. I have attended Q Turkey's educational programs, and I am currently actively participating in the Womanium training. That's all. Let's move on to algorithm. Quantum Boolean image processing. What is this? Is a technique in quantum image processing that aims to perform operations on images using Boolean logic. This method seeks to improve and accelerate image processing tasks by leveraging the power of quantum mechanics. Before the steps, first we converted the image to 32 by 32. Step 1, bit plane processing, bit plane slicing. Bit planes, each pixel of an image typically has an 8-bit value. Each bit plane is considered as 8 separate binary images. The representation of binary images. First, we print the pixels of each bit plane. We express each pixel value in binary format. We specifically save this binary format to a .txt file. Step 2, qubit representation. Using our .txt file, we converted the bits to qubits. If a pixel value is 0, the corresponding qubit is in the cat0 state. If the state's pixel value is 1, the corresponding qubit is in the cat1 state.
Okay.
Step 3, quantum circuit design. We need as many qubits as the number of classical bits, and if there is an 1 in the corresponding position in the binary representation, we apply an X gate to the qubit. Otherwise, we do nothing to the qubit. Finally, we design the quantum circuit. Similarly, we save it to a .txt file. The images. First images is the binary representation of pixel values, and the second is the representation of our qubit in circuit. We use the file system because to access the slice images we generate directly and ensure the not overlap. The reason X-gate are applied to each qubit is to leverage and superposition and correlation properties of quantum mechanics in processing classical pixel values. Yes, that's all.
Thank you.
Thank you.
So I will like to continue that. So as we were working together, I am Siddhant. So continuing about QBIP, I actually sent a paper also regarding it, an extra paper regarding how it could be beneficial compared to how FRQI and NEQR, because that paper discusses about some fatal issues that could be present in FRQI and NEQR. Basically regarding how, basically how you just asked, right? That can we reconstruct the image back? Can we get the image back from the quantum circuit? So basically that paper discusses that how FRQI and NEQR is not able to do that as efficiently, and QBIP is able to do that. But again, as you did basically explain now, how we require the same number of qubits as the number of bits are being utilized to represent the image. So if I just share my screen, I can show the implementation that I'm talking about. So we have two implementations. One implementation was done by me, another was done by Asyude. Now, one second. Can you see my screen?
Yes, I can see now.
Okay. So let's say this is basically the entire pipeline, basically. So this is the bit slicing part where we get all the red bit plane, green bit plane, and the blue bit plane, as there are three channels in an image. And we consider that there are 8 bits per pixel. Hence, we process it one by one. We process the red bit plane using the quantum circuits, the green bit plane independently, and the blue bit plane independently. And then we reassemble everything back into getting the final image by doing np.stack. Now, let's just see one image. like I took the Lena image, which is very popularly known for like quantum image processing task. So I took this image, I put it in the pipeline, and then as it's returning the where is this? Yes, it's returning the reconstructed image back, and so I call the function, and then I get the basically the output image. This is the output image basically. This is actually the so the input image and the output image have 99%
Research.
structure similarity. Yes.
Nice.
So, and this is one of the dataset images that was there.
Yes.
So if we take that and put it in the pipeline, we get a 99.6% structural similarity, which is pretty good.
Yes.
But one of the fatalities of QBIP, I will say, is that it takes time. It takes time to load the image, as it took, I guess, 5 minutes
Mm.
for one image.
Oh,
Because as we just discussed, the number of qubits required would be the same as the number of bits required. Hence, that would be an issue that would be arising if we try to load images.
yes.
So that is the. Other than that, FRQI and EQR, the issue that I was trying to state was that if I can show the paper, if it's okay,
Okay.
it's, just give me 1 second. Um, yeah, got the paper.
Our image size is 70, 77 pixel. Video.
Can you repeat? Sorry.
Our image size is 70 pixel.
Yeah. The image size is same.
Mhm.
So I wanted to show this paper. So in this paper, they talk about the truth of how the internal image representation works,
Mhm.
and I will just go to the output of that, like what they were trying to state.
Mhm.
So yeah,
Do
this
you
is
want
what you can see.
this paper? Ah,
Pardon?
yes. Okay, you can continue.
Yes. So this is the original image that they took, and they put it in FRQI, and they
Mhm.
tried to get the image out of by measuring it. So this is what they got by measuring the circuit. They got a lot of gibberish noise basically, and NEQR also give a lot of gibberish noise. QBIP didn't give so, because we are as the number of qubits is equal to the number of bits, so
Yeah.
there is no data loss as such. That is the major part. And another thing is that the time. FRQI took so much time, and QBIP took way less
Mm.
comparatively, as you can see. So this is something that was that I wanted to share initially when we were doing the loading of the images.
Mhm.
As according to this paper, uh, like quantum image processing is right now too early to load images and do processing on it very efficiently. So that is the. But I saw some papers that prefer to do it, but they prefer to do it either using NEQR,
Yes.
because some of them say that there is some encoding happening that is actually useful if we take that encoded representation in our machine learning algorithm that we will use later on. Maybe that could be useful. And QBIP also, because the entire data stays intact. So we can do that. Both of them are okay.
Okay.
So another thing that I had to say was that basically if you are trying for, like, so I went to the data set, like the actual data set that was the,
Yes.
like, can you see?
Yes.
Yes. So I went to the code section, like what are the, so this person, the person who made the data set, he published a lot of notebooks also regarding how they could like how we could basically utilize the data set for various tasks.
Mhm.
And some, like, so we are doing corner detection, right? So corner detection could be represented as a regression problem. So I went to the regression problem type of the notebook,
Mhm.
and I saw the notebook, and basically this is how the this is how, wait a second.
Mm.
uh, yeah, these dots, if you can see, these are the, like, the corner detected. Yes. So basically, our main goal would be to get these corners, right?
Yes.
So I was basically trying to like do this, but with quantum machine learning,
Mm-hmm.
like independently, but in a way that uh, utilizes classical machine learning also. So basically, a hybrid version where I'm using quantum also and classical also. So there will be a classical pipeline that is actually loading the images and basically processing it, and then there is a quantum layer that comes in between, which basically does the corner prediction, like the corner detection part. That is something that I was looking into, that I was doing independently by myself, and I got comparable results. So I was thinking to share this with you, as it could be useful to set a benchmark. Like if you see here, where is it? Oh, 1 second. Yeah, they got 90% test accuracy.
Mm-hmm.
So the quantum model, as much as I remember, it got 92.8. So like 2% more.
Yeah.
So that was something there that I wanted to share. Another thing that was there was that I like, as it's a regression problem, they also try to utilize, instead of deep learning, they try to utilize classical machine learning, like k nearest neighbors and something like that, like KNN.
Yeah.
And
Other
there is,
SVM we can use.
pardon?
To classify, we can use SVM, I think.
Yes, yes,
Yes.
yes. So for this for regression part specifically, there is KNN that could be utilized too. Like it can be utilized for classification also and regression both.
Mm.
So I was looking into that too, and KNN got a 90% accuracy, like normal KNN, like classical KNN got a 90% accuracy.
Mm.
And there is something known as quantum KNN also that exists, which utilizes the quantum properties of superposition to
Mhm.
basically do the regression of the values. So this is the paper that I'm talking about. Uh, if you can see,
Yes, we can see.
yes, yeah. So quantum k nearest neighbors algorithm, quantum KNN. So I utilize this algorithm as well, and that is also something that's uh, and this also got, actually it got the same accuracy as KNN. Like this and quantum KNN and KNN, both of them got same accuracy at the end of the day. So that is something that I also wanted to share. So but and both of them, the common part about both of them is that there is a classical image loading part, and later on we utilize the quantum layers to do the regression or classification.
Maybe,
So
maybe,
that is all I wanted to share that I did this week.
okay. I
Yes,
understand. As I
thank you.
understand, you want to use a classic hybrid model, quantum and classical, combine the classical and quantum parts. Am I right?
Yeah, like combining the classical part for the loading and pre-processing, and then utilizing the quantum part for getting the outputs.
Um, but I think my purpose is to compare the results, all of the models, loading models. But I want to think about that. Maybe we can use your model in the next step and to compare the results. And thank you for your work.
Yes, yes.
Thank
Yeah, I
you.
understand. Yes.
Okay. I will continue. Uh, Actually, I share all of you the original codes like modern images models, and I have some codes. Maybe everybody see that NARQR, QBIP models. There is three models codes. Everybody can use these codes for loading the images. Maybe help all of you. And actually, my purpose is to going to the next step the quantum corner detection part of our project. And you know, our purpose is detect the corner detection. Our purpose is detection the corners, and I want to follow this paper. Firstly, first step is loading the images using for model. After that, fast corner detection circuit implement. After that, using the QML to classify the images. And yes, you know, first step is, but there is some unimplemented parts in the models. But I want to explain again the corner detection part. Maybe some of them continue with that. And steps of the quantum fast corner detection algorithm is the first step is select the neighbor of the and choose the two threshold value. We are selecting a part in the images. The center of the images is named as a nucleus inside the area. There are three types area, for example, like that, A and B and C. The C is the corner and B is the edge. A is there is nothing, corner or edge. After select the corner, any part of the images, we are select the dimension 3 pixel to implement the corner detection. The 3 pixel, we are according to the 3 pixel, we are select the neighborhood and by radius 3 pixel and choose the two threshold value by using contrast value according to the accuracy value. And second, in the third step, corner going to be detected by using this value. Consecutive endpoints like this 1, 2, 3, 4, 5, 6. This is the endpoint in the neighborhood. And grayscale value difference with the nucleus p value is greater than the first threshold value is selected the corner. We are select the corner as a corner is another and n is great, and then p is determined as a corner point. First two step of the corner detection algorithm is implemented in this paper. Our purpose is implement in the second step this part, and you can, if you implement the first part of the loading images, you can continue the second step, fast corner detection algorithm, by using this paper. And yes, I think first and second group continue to work loading images, and third and fourth has to do second step of the our work. Yes. Is there any question? I will share our meetings. Is there any question?
Can you send this paper? We will like to read this.
Yes, I will send.
Okay.
Okay.
One thing that I wanted to ask is that if there is an implementation, like according to this paper, they have done it, right? Like they have done this quantum corner detection, correct?
Yeah,
So,
there is enough explanation in this paper.
okay.
Yes,
Because I was thinking maybe we can contact the authors regarding how, like adding if they have any code implementation that they would like to share or something.
yes. If you have any question, you can ask me directly or DM. It doesn't matter. We can meet online. We can arrange online meeting. There is no problem.
Yes, yes. Okay.
Okay. Is there another question?
Yes, I have a question. Where do you store the recordings?
Yes, I will share you, all of you. Sorry, first meeting, I cannot share because there is a problem. There was a problem in my computer. Sorry for that. But now I will share all of you.
Yeah, no problem. Thank you.
Okay. Is there any question?
I have a question about the GitHub, the repository that you shared.
Yes.
How will be the branching and PR policy? We should code directly on the main branch, code in different branch, and after do a PR to put everything on the main branch. You have any organization that we should follow, any steps that we should follow about the GitHub repository?
Actually, I don't think about this, but maybe branching is makes sense, I think, because
Okay.
we are developing for models. Yes, branching makes sense.
Okay. Thank you.
Not.
I have one more question.
Yes.
The team that I'm with is not available, I think, because I've written to him, but he didn't answer. So, what do we do?
Yeah, yes. Good question. Finally, I want to say that everybody in the project groups needs to take responsibility. All the work not to be placed on a single person. Is there any problem? You can share me. I can change the groups. Others, I can do another things. Yes, did you talk about the region?
Well, I've already written to him, but I didn't get a response from him.
Okay. I will do something about that. Thank you for your question.
You're welcome.
Okay. Is there any question?
I also have a short question.
Okay.
While we were reading the papers,
Mhm.
if we am stuck at some place, we can ask about it to you, right?
Yes, you can ask.
Okay, thank you very much.
No problem. We can arrange any meeting about the problem, except from this meeting. Yes, we can solve the problem. We try to solve problem. Okay.
Yeah, one more question just for the clarification.
Yeah.
So the first step was to load the images and try out all the different techniques, the 4 techniques we have, and the purpose of this step was to try out all those techniques and just make a comparison,
Accuracy.
like which technique is better, which is worse, and which one is better in which case, and etc. So just to make a comparison, right?
Yes, my comparison. And also in this paper, an NAQR technique model is used. Maybe this paper helps to first group to implement the model. And also, as I said, there is a course of all of the models. Maybe it can help all of you.
Thank you.
Not a problem. Okay, next week we can again arrange a meeting to talk about what we did. And yes, the same time, same day is okay, all of you? Next week? okay, we can talk in the Discord. We can arrange and okay. Thank you. Good work, everybody. Thank you all of your work and all of efforts. And see you next time. What you want, what you time, anytime you can share your problem, your question with me on DM or other networks. Okay. See you.
Thank you very much for your efforts.
Thank
Have a
you.
nice
Bye
weekend.
bye.
Next weekend.